Every once in a while, you may notice that your faucet isn't flowing so well, or that your shower head is spraying unevenly. Upon closer inspection, you might notice that there's some white buildup obstructing the flow of water. What's with that? Where did this gunk come from? Unless you put it there, the only place this buildup could have come from is the water itself. Even though it looks clear, the water coming into our houses is loaded with different dissolved ions and compounds. When the temperature or concentration of the solution changes, these ions and compounds emerge out of solution in their solid form. The temperatures or concentrations at which these chemicals or solutes emerge stem from each solute's solubility, or ability to be dissolved in a given volume of a solvent at a given temperature. Solubility for a compound is expressed in terms of molarity, moles per liter, and is temperature dependent. Generally, increasing temperature increases a substance's solubility. When you run cold water through a faucet or decrease the flow to a trickle, the dissolved chemicals become less soluble and form solids, aka pesky buildup. A substance is considered to be soluble when its solubility is greater than 1 gram per 100 grams of solvent. This means that 1 gram of substance can completely dissolve and dissociate into ions in 100 grams of solvent. Sodium chloride, NaCl, is very soluble in water. A substance is considered to be insoluble when its solubility is less than 0.1 grams per 100 grams of solvent. Calcium sulfate, CaSO4, one of the main ingredients in water buildup, is insoluble in water. Anything in between is considered slightly soluble. When a solution of a given volume has the maximum amount of solid dissolved in it, it is said to be saturated. For soluble compounds, saturation occurs at high concentrations. For insoluble compounds, saturation happens at very low concentrations. Let's go into our virtual lab and do some little experiments with solubility. For any compound that goes into solution, we know that it will break down into its constituent ions. For example, if we put compound AB2 into water, it will break into one A2 plus ion and two B minus ions. While these ions are swimming around in solution, there is a possibility that they will collide with each other and reform into a solid. We can show the tendency of this reaction to go both forwards and backwards by using a double-headed arrow. Eventually, a dynamic equilibrium will be reached. We can write an equilibrium expression for this by using the law of mass action. If you're a little fuzzy on how to do that, watch the video on dynamic equilibrium and determining the value of K, the equilibrium constant. Remember that when writing laws of mass action, you don't have to consider solids or liquids because their quantities cannot be expressed in terms of concentration. So, we get to leave out the solid form of AB2. Ksp equals the concentration of A2 plus times the concentration of B minus squared. Similar to other equilibrium expressions you may have encountered, the symbol K is used for the equilibrium constant. We use Ksp to show that this equilibrium is specific to solubility. The proper term for Ksp is solubility product constant, or solubility constant.